Just like we did with capacitors, we can take resistors and add them into a circuit. There are many different combinations we can produce depending on how we wire our circuit and what we want our output to be. Say we have a simple circuit that has 3 resistors connected in a line. These are said to be connected in series. The current will leave the positive terminal of the battery and travel through each resistor in sequence. This means that the current going through each resistor will be the same. We can measure the voltage across each resistor with a voltmeter and label them as V1, V2, and V3. The total voltage of all of the resistors then will be equal to the voltage of the battery. According to Ohm's law, the voltage of the battery is equal to the total current times the total resistance. So we can take Ohm's law for each part of the circuit and find the voltage of the battery equal to the current in resistor 1 times the resistance of resistor 1, plus the current in resistor 2 times the resistance of resistor 2, plus the current in resistor 3 times the resistance of resistor 3. Since the current is the same across each resistor, we can factor out the current. The voltage of the battery is equal to the current times the sum of the resistances, and it is also equal to the total current times the total resistance. That must mean that the total resistance is equal to the sum of all of the resistances. So our total series resistance is the sum of all the resistors in that series. This is true no matter how many resistors you have. So you can think of all of the resistors in that series as equivalent to one big resistor. Suppose a battery has a voltage output of 12 volts with resistances of 1, 6, and 13 ohms in series. What is the total resistance? This is a nice simple math problem since the total resistance for 3 resistors in series is the sum of each resistor. Add them all up and we get a total resistance of 20 ohms. So then what is the current through the circuit? Well, voltage is equal to the current times the total resistance, so we can arrange Ohm's law to solve for the current. Our voltage of 12 is then divided by our total resistance of 20 ohms to give us 0.6 amps. Well then what is the voltage drop across each resistor? Ohm's law still applies here, so we can use our current and the resistance of each resistor to solve for the voltage. The first resistor's resistance is 1 ohm, so the voltage drop of a 0.6 amp current is 0.6 volts. The second resistor's resistance is 6 ohms, and so the voltage drop across the second resistor is 3.6 volts. And the third resistance is 13 ohms, giving a voltage drop of 7.8 volts. We can add up our 3 voltage drops and find the total of 12 volts, which is what we would expect from a 12-volt battery. Then how much power is dissipated across each resistor? Well, we talked about power being equal to the current times the voltage. Since the current is the same through each resistor, we can substitute in Ohm's law when solved for voltage, and use the power equal to the current squared times the resistance. We can just use the values for our current and our resistors to find 0.36 watts of power dissipated from the first resistor, 2.16 watts from the second, and 4.68 watts from the third. If we compare the total power from all of the resistors to the total power output of our battery, we find that they are the same. This makes sense because power is energy per unit of time, and so must follow along the conservation of energy. So the total power output from the battery must be equal to the total power dissipated by the resistors. Connecting resistors in parallel means that each one is connected directly through the voltage source. So the current flowing through the wire could turn and go through the first resistor, or it could continue on and go through the second resistor, or it could keep going on and flow through the third resistor. In our series circuit, the same amount of current went through each resistor because that was the only place they had to go. In a parallel circuit, the current going through each resistor is different. Now, which resistor do you think is going to have the most current going through it? Current is going to follow the path of least resistance. Now, the wires in a parallel circuit are all equal potential, so the potential across each resistor is going to be the same, but the current will be different. So we can say now that the total current is equal to the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3. We can still say that the total voltage is equal to the total current times the equivalent resistance. Ohm's law is pretty handy, so we can substitute that in for the current through each resistor. So the total current is equal to the voltage across resistor 1 divided by the resistance of resistor 1, plus the voltage across resistor 2 divided by the resistance of resistor 2, plus the voltage across resistor 3 divided by the resistance of resistor 3. And since voltage is constant, we can factor that out and find the voltage times the sum of the inverses of all of the resistances. Now again, going back to the total voltage equal to the total current times the total resistance, we can see that we can set them equal. That gives us the inverse of the total resistance equal to the sum of the inverses of all of the resistors. So let's take our battery with our 12 volts and our resistors of 1, 6, and 13 ohms and put them in parallel. What is the total resistance? The total resistance for 3 resistors in parallel is the sum of the inverse resistance of each resistor. Add them all up and punch them into the calculator correctly, and we get a total resistance of 0.804 ohms. As you might expect, the total resistance is less than the smallest individual resistance. So what current goes through the circuit? Well, voltage is equal to the current times the total resistance, so we can rearrange Ohm's law to solve for the current. So our voltage of 12 is divided by our total resistance of 0.804 ohms to give us 14.92 amps. Notice this is much larger than the current of 0.6 amps we found for the same resistors that were connected in series. Well, then what is the current across each resistor? Ohm's law still applies here, so we can use our voltage and resistance of each resistor to solve for current. The first resistor's resistance is 1 ohm, so with a voltage of 12 volts, the current will be 12 amps. The second resistor's resistance is 6 ohms, so the current across the second resistor is 2 amps. And the third resistance is 13 ohms, giving a current of 0.92 amps. Now, conservation of charge tells us that the total current of the entire circuit must be equal to the total current of all of the resistors. And in this case, the sum of all our currents does in fact equal what we got as a total current in the last problem. Then how much power is dissipated across each resistor? Well, we talked about power being equal to current times the voltage, so we can substitute in Ohm's law and solve for current and use power equal to voltage squared divided by the resistance. We can just use the values for our voltage and our resistors to find 144 watts of power dissipated from the first resistor, 24 watts from the second, and 11.1 watts from the third. So comparing the total power from all the resistors to the total power output of our battery, we find that they are the same. Again, making sense because power energy per unit of time, so we must follow along with the conservation of energy. So as a review, to find the total resistance of resistors in series, you simply add the resistance of each resistor. To find the total resistance of resistors in parallel, you have to take the inverse of each resistance, add that up, and then take the inverse of that particular sum to find the total resistance in parallel. In series, current is the same through each resistor, while voltage is divided across the resistors. But in parallel, the voltage is the same and the total current is divided across the resistors. Of course, not all circuits are nice and simple in either series or parallel circuits. What we have to do is break down the different parts and figure out the equivalent resistance of each individual part. Okay, so find the total resistance. Here we have 3 resistors. R2 and R3 are in parallel with each other, and this system is in series with R1. We can treat the parallel system as one resistor if we find the resistance of that whole system. And since it is in series with resistor 1, those two values will simply add up to the total resistance. The inverse of the total resistance for resistors in parallel is found by adding together the individual inverse resistances. So the inverse of 6 ohms plus the inverse of 13 ohms, inversed, gives you 4.11 ohms of resistance in that part of the circuit. Now we just take that and add it to the first resistor's resistance, since it is in series, and find the total resistance of the circuit to be 5.11 ohms. Notice this resistance is neither more nor less than any of the individual resistances. It lies somewhere in the middle. So find the IR drop in resistor 1. Well, we know that the IR drop is found using Ohm's law. We also know that since resistor 1 is in series, the full current is going to flow through it. In order to find the total current, we need to use another version of Ohm's law by taking the voltage of 12 volts supplied by the battery divided by the total resistance, which we just found to be 5.11 ohms. This gives us a total current of 2.35 amps. This can be used in the first version of Ohm's law to find 2.35 volts. This means that the voltage supplied to the resistors 2 and 3 is less than the total voltage by 2.35 volts. So find the current through R2. Well, we must know the voltage that is applied to it, and since resistor 2 is in parallel with resistor 3, we have to take that into account. Since these two are in series with resistor 1, we need to subtract the voltage drop through resistor 1 from the total battery voltage. So the current through resistor 2 is equal to the voltage through the parallel portion of the circuit divided by the resistance of resistor 2, which is 1.61 amps. So find the power dissipated by resistor 2. Well, power is still current squared times the resistance. We found the current going through the resistor 2, and we're given the resistance. So the power dissipated by resistor 2 is 15.5 watts.